All right, hello, and welcome to day 3 of the Regression Challenge. Yay! So in the first day, we learned about different types of regression, Poisson regression, linear regression, and logistic regression. And yesterday, on Tuesday, my time, we learned about how to fit a model and then evaluate it using diagnostic plots. And today we're going to fit a model and we're going to look at the model and we're going to learn how to interpret it and what all the different pieces mean. And we're going to go through the output sort of line by line and really drill down into what all the little bits are. But to do that, we need to think about what a coefficient is. And I will say I'm using new recording software today, so if things look a little bit different, that's why. So if you ever took a math course where you learned about how to represent a line, and the formula we were taught was y, so the output on the y-axis, equals m times x, where x is your x value that you're inputting, and m is the slope of the line, plus b, where b is the intercept. So the coefficient is, if you're thinking of lines in that way, the slope of the line. So another way to think of it, because not all regression is linear, and for non-linear regression, the slope of the line is a much less meaningful thing. Like, what does the slope of the line in logistic regression mean? That's less apparent. So another way to think about it that's more general is that the coefficient value is for every increase of the input value by 1 unit. So if we're trying to figure out the weight of a cantaloupe and our input value is if we're trying to figure out the price of a cantaloupe and the input value is the cantaloupe's weight, right, then the coefficient would be the value that you multiply the weight by and then add whatever the intercept is, and then out you get the predicted output. So for every increase of the input value by 1 unit, whatever unit that is, the output value will change by whatever number the coefficient is, units. So it's just a way of representing the strength of the relationship between your input and your output, and also the direction of the relationship. So if it's positive, then increasing the input will increase the output. If it's negative, then increasing the input will decrease the output. So we're going to look at a data set of hard drives. This was actually put together by a company called Backblaze that does backups. And they have a lot of information on a lot of different hard drives. And I'm interested in predicting whether or not a hard drive will fail based on another quality it has. So I am using the thing that's in the column Smart 1 normalized in the data set. And I looked on Wikipedia to find out about the SMART test. And the first test is the read error rate. So you want a low read error rate because that means when you go to read the disk, you don't get errors as often. And if you have a high read error rate, when you go to read the disk, you get a lot of errors. And my intuition is that as your read error rate increases, you should get more hard drives that fail. Yeah, I don't know a whole lot about hardware, so I'm not an expert in this field, but that seems reasonable to me. So we're looking at whether or not a hard drive fails, which is categorical and has 2 values. So I'm going to use the binomial family when I fit my logistic regression model. Some people have been asking about what you do when you have multiple outputs, and the answer is that's slightly more complicated than we're gonna cover in the challenge, but you would not use the binomial family because the binomial family is for 2 outputs, and you can tell because it has the word bi in it for 2. Ooh, excuse me, I hit something on my desk. So we're gonna fit a model where the output failure is going to be predicted by the input Smart 1 normalized, which is that read error rate value. We're going to use the hard drives data that we read in, and we're going to use the binomial family for our linking function. And at this point, I would recommend that you do a diagnostic plot, but I ended up not doing a diagnostic plot because I have 100,000 points, and it just took a really long time to converge, so I got bored and decided not to do it. But you should do it. The data set y'all are going to be working with is this camera's data set, which only has 1,000 data points, so it should not be as big of a problem as it was for me. All right, and then once we have our model, we're going to look at our summary. So I'm just going to scroll through for a little bit and let you see the amount of information that's here. This is very rich, and it tells us a lot about our model. and we're going to go through line by line and talk about what each of these things are. And all of this is written down here, so you can come back and look at it later. But we're just gonna sort of sit here, and I'll move my mouse around, which should be highlighted and easier for you guys to see. So this first bit, call, just tells you what you typed in when you built your model. So this is exactly the same as this. And it can be useful to check if like maybe you made a typo. If you're comparing multiple models, make sure you got the model that you think you got. But usually you can ignore it. The residuals here, this is a quick way to check whether or not your residuals are normally distributed. So you do want them to be normally distributed for Poisson regression and linear regression. For logistic regression, it doesn't matter as much. So this would be a huge warning sign if you were doing linear Poisson regression, but also you would have seen that in your diagnostic plots. So what you want to see here is you want the median to be near 0 because the mean will always be 0 due to the way that these are fitted. They're fitted using ordinary least squares, if you care. And you want the first quartile and third quartile to be near each other, but you want this one to be positive and this one to be negative. So the fact that these are both negative suggests that we have a real big skew in our data, and we have some major outliers. And then this is just the minimum and the maximum, so this gives you the range. So this is a good way of just sort of like checking and making sure your residuals are normal, and that's all you need to do there. This tells us about all the different coefficients, and if you are using multiple different things that you're predicting, you're going to have more lines here. And if you're predicting something that's categorical that has, if you're using as a predictor something that's categorical that has a lot of levels, so if you're saying like you're trying to predict weight of a dog and you're using the dog's age and the dog's breed, and you have 3 dog breeds, you're going to see dog breed 3 times for each of the you're going to see dog breed 2 times, and that'll tell you the difference between the whatever dog breed got listed first and is considered the default and the other 2. So we're just going to ignore the z-value and the p-value, and we're also going to ignore the significant codes. So you can see that I've got some stars here, and if I were doing, good science, and I had planned this experiment from day 1, and I knew this was the analysis I was going to do on it, and this is the only analysis I did on this data set, this would be right, and I could rely on these. But if you do more than one if you do more than one statistical hypothesis test, it changes the p-value. So because most data scientists tend to do multiple tests on the same data set, these aren't actually accurate after the first test, right? So I would recommend just not even considering them, don't even think about them, just ignore them. Unless you're a scientist and you're doing something very specific. So this is the intercept. So this tells us if it's a linear regression, what y should be when x is 0. So when all of the coefficients, all of our input terms are set to 0, what's our output going to be? In logistic regression, it just sort of tells us about if there's imbalance in our classes. So this tells us how far we are from the probability of each of the 2 classes being 0.5, right? So this will be closer to 0 the closer our 2 classes are to balanced, if that makes sense. So if there's a 50% chance that we'll see group A and a 50% chance we'll see group B, then this will be near 0 and this will be very large. So because this is very big and you don't need to worry about the sign too much, we can tell that we probably have imbalanced classes. And because the standard error is pretty small, so sort of the rule of thumb that I use is that you can generally rely on this if the standard error is about 1/10 of the estimate and the estimate plus or minus the standard error doesn't overlap with 0. Because that's the case here, I can say, yeah, our classes are probably really imbalanced. And then this is our input variable, right? Smart 1 normalized. And this tells us sort of the most likely change. So for every increase of 1 in smart input normalized. So every time the error rate increases 1, we get this change in the log odds, which is what the logistic regression puts out. But this is really close to 0, you might have noticed. And also our standard error is not 1/10 of this. It's, I don't know, like 50% of that. So I don't really trust this value. I think that probably this isn't a very good predictor. This line, so this is just a key to the p-values that we're ignoring. This line will only show up if you are doing binomial regression or Poisson regression, and it's just letting you know that they're adding a term to the fitting process, and you don't need to worry about it. This tells you, so both null deviance and residual deviance tell you how good your model is at describing what's in the data set, right? So lower is better. You want less deviance rather than more deviance. And null deviance is when you take out everything but the intercept. So this is how good our model is at describing what's going on our data if the only thing we consider is the intercept. And the thing that you really want to look out for is you want to see if the residual deviance is much lower than the null deviance, because that means the term or terms that you added is really improving your model fit, and you're getting a lot more information out of your data set. And as you can see, it's 147 and it goes down to 141, and that's practically no change. You can see some, especially if your predictors are very informative, you can see like an order of magnitude change in these values. So I saw that this was very low. I didn't really trust it, and I can see that adding it isn't really helping us that much, so probably not a great predictor. The AIC is I don't actually know how it's said. It's like I've thought for the longest time this was pronounced Alki, and it's not. I think it's a Kaiki. Everyone just says AIC. Nobody ever says the whole thing. Is a measure of sort of similarly how well your model is capturing information in the from the underlying data set. And the thing that you want to use this for is when you're comparing models. So if I then fit a second model, let's say I was thinking maybe SMART 2 normalized would be very informative, and I wanted to see if that model was more informative than this one, I could compare the AICs, and whichever one was lower is probably capturing more of the change in the data set. It is more often used when you're adding terms, and you want to see if adding a term is helping your model capture the variance in the data set better. Finally, number Fisher scoring iterations. This is just sort of a measure of how long your model took to converge. So the bigger it is, generally the longer it took your model to converge. You don't need to worry about it. If you're seeing this at all, it means your model converged. Good job. You can go home. Okay. So we can actually, and this is just the same thing again, and I talk about it with relationship to this particular data set. And if we plot our data set, if we plot our data set, we can see that, actually let me zoom out a little bit, zoom, a little bit more. There you go. So you can see, so these are the drives that were failures, and these are the drives that were not failures. And our model is pretty much just always predicting that a drive is not going to fail, because most drives don't fail, right? They're really, really imbalanced classes. And that's what we saw from having the intercept be so far from 0. So particularly for logistic regression, that's what that information tells you. And we can also see that this axis, there's no change in the y over this axis. So remember, this was very close to 0, and it's not exactly going to be sloped because it's logistic regression, not linear regression, but it ain't moving much as this changes. So that's pretty much it. That's all that goes into interpreting a model. And you guys are going to work with, I've already read it in for you, this camera's data set that's much smaller, so you shouldn't have a problem doing all the diagnostic plots. And just, pick a variable that's interesting to you and try and predict it. So maybe release date, which would be Poisson regression. Maybe, actually a lot of these I think would probably be Poisson regression rather than linear regression. Although somebody did have a question today, which was when can you use linear regression instead of Poisson regression? And it's usually when you have more than 1,000 cases or so, or 10,000. It's sort of a judgment call. But for this data set, you could probably use linear regression rather than Poisson regression if you wanted. All right, so that's it for today, and I look forward to seeing your guys' work. And feel free to leave me questions. You can leave them on the forums. You can leave them on the notebooks. I've tried to be pretty good about answering them. And I will see you guys tomorrow. Later.